Hello class, I'm going to go over section 6.3, the central limit theorem. So this starts on page 152 of our course workbook for statistics. Okay, so let's see. So I'm going to read over some of this material, the vocabulary, and then some of this I'm going to kind of just gloss over because it's theoretical, and I'm going to go to the problem. So I don't think some of this is really needed. But I'm going to show you how to work some of the problems. So it says that in addition to knowing how individual data values vary about the mean for a population, statisticians are interested in knowing how the means of samples of the same size taken from the population vary about the population mean. So they have distributions of sampling means. A sampling distribution of sample means is a distribution obtained by using the means computed from random samples of a specific size taken from a population. Sampling error is the difference between the sample measure and the corresponding population measure due to the fact that the sample is not a perfect representation of the population. Then they list some properties of the distribution of sample means. The mean of the sample means will be the same as the population mean. The standard deviation of the sample means will be smaller than the standard deviation of the population and will be equal to the population standard deviation divided by the square root of the sample size. Okay. And then they have an example here, they have a little picture representation. So this is kind of where I'm going to kind of gloss over this, and I'll let you read over that and look over that. Same thing on the second page here. Okay, but I am going to read, before I start the problems here on page 154, I will read this top part, the central limit theorem. So as the sample size n increases without limit, the shape of the distribution of the sample means taken with replacement from a population with mean mu and standard deviation sigma will approach a normal distribution. As previously shown, this distribution will have a mean mu and a standard deviation of sigma divided by the square root of n. The central limit theorem can be used to answer questions about sample means in the same manner that the normal distribution can be used to answer questions about individual values. So a new formula must be used for the z values. So we have z is equal to, and this is your sample means is x bar minus mu divided by sigma divided by the square root of n. Okay. And so you saw that here, right? Standard deviation, sigma square root of n, they're mentioning that. Okay, so let's see. Let me see, I had also a page here, a copy of from your ebook. Let me just see. A lot of this from the workbook is taken from the ebook. It does say here that notice that x bar is the sample mean, and the denominator must be adjusted since means are being used instead of individual data values. Yeah, so in section 6.2 we use individual data values, okay? And that's not the case here. Denominator is the standard deviation of the sample means. So this they're calling this sample means. That's how this is referred to. And then also, if I continue reading down here, it says that if a large number of samples of a given size are selected from a normally distributed population, or if a large number of samples of a given size that's greater than or equal to size 30 are selected from a population that is not normally distributed, and the sample means are computed, then the distribution of sample means will look like the one shown. And let's see. Let's see, let me look at my book. I don't have that other page. This is 6.3. Yeah, so most of this that I went through, it's in your ebook, most of that. And what I'm reading now, says shown in figure 6-33. So that's a picture of what that was looking at. That's from your ebook. So we did a problem kind of looking similar to that, right? In our section 6.2 with mean and then mean plus or minus, right? K times, and I think we were using K times sigma. So I didn't use X bar. Here they're using X bar because we're in 6.3 now. But that looks similar, right? We did a problem like that in the video, right, for section 6.2. And it does say here that, I'm going to read this out loud from your ebook. Let's see. So it says it's important to remember two things when you use a central limit theorem. When the original variable is normally distributed, the distribution of the sample means will be normally distributed for any sample size n. And when the distribution of the original variable is not normal, sample size of 30 or more is needed to use a normal distribution to approximate the distribution of the sample means. The larger the sample, then the better the approximation will be. Okay. All right. Okay. And then they have the problems that we're going to work. Yeah. And then when it comes to towards the end, they talk about the finite population correct factor that's listed as optional. And so we don't do any problems with regards to that. So we're going to kind of gloss over that. Okay. So let me show you these problems then. All right. So we're on the bottom of page 154. So we have that hours of television. A.C. Nielsen reported that children between the ages of 2 and 5 watch an average of 25 hours of television per week. So here's your 25. This is 25 hours. And this is your mu. And it's got the keyword, right? Average, just like your mu. Assume the variable is normally distributed and the standard deviation is 3 hours. Okay, so remember the units have to be the same. So this looks good, hours and hours. If 20 children, so here's where the n comes in. See this new formula? Here's where the n comes in, because before in 6.2 it was understood to be one individually. Now we've got a group, n is 20. And the keyword is it tells you that they're randomly selected. That's really important. That helps you remember this. Find the probability. So that's the area. Probability is area. Find the probability, so it's area, that the mean of the number of hours they watch television will be greater than 26.3. So you see here's the 26.3 and this is in hours. And I'm going to call this X bar because they do mention that the mean of the number of hours, and remember this right here in the formula is sample mean. So I'm going to just call that X bar instead of just X, okay? And we're trying to find the area. And this is a good place to put it. It's anywhere on the right side because this is 25. You don't want to put on this side. 26.3 is, greater than 25. So it needs to be, it doesn't have to be right here. I mean, if you wanted to make the line here, you could, or here, but definitely has to be somewhere on the right side. Okay. All right. So what we'll have to do is we'll have to use a new formula. Okay. So that would be this, that z is equal to sample means minus mu divided by, and I'm going to write it sideways. I'm going to put standard deviation divided by square root of n. And I'm going to do this because usually in the calculator you have to do that to take this outside of this radical and then close it. Okay. Okay, so now we're going to sub, which is short for substitute. So x bar is right here. That's the 26.3, right? And it's really small. You can see that there. So it's 26.3 minus mu. Here's your mu, 25. And then sigma was 3, right? Right here. Divided by the square root of n, which is n was 20. Remember, 20 children. And you see how I have that there. And then you would kind of press this out on the calculator, the arrow, and then close it. Okay, so, and you can type this in all in one swoop. You just have to use your parentheses. So parentheses right above 8 and 9 are the parentheses. Right above 8 and 9. So parentheses 26.3, take away 25, close parentheses, divided by open parentheses, 3 divided by, okay, now the square root, you want to hit the second button and you want to hit the x squared button because that's where you have, see that radical? So you hit second and then x squared. And see that pops up. The radical square root of 20. And then see right here, you need to take that out of that bar. So that's why I use, see this arrow right here? So I use this arrow, see, to take that off. And then close the parentheses and then hit enter. And that gives you 1.93792. And remember, this is a z. Remember, z's are rounded to the nearest hundreds. Okay, and then look at the number to the right. Is that 5 or more? Yep, it's a 7. So add 1 to that. So we're looking at 1.94. So there's your z. Okay, and z's are rounded to the nearest hundreds. Okay, so that's like part 1, right? Okay, now you have a new picture. So now your mu is 0, and now your sigma is 1. And then now, trying to find this area still, but now this is not sample means. Now this is z, which is 1.94. Okay. And so when we're going to use a table first, but when we set it up for both of them, whether we use the calculator or the table, you start off with probability, and it was x bar sample means is greater than this, and that was 26.3. And then you ran it and transformed it through the formula. And then probability, now it's a z is greater than 1.94. And then when we use the table, we're using the table. When you use a table, you can only use a table, and you're looking at on the table areas to the left. So the whole area underneath the curve is 1 or 100% or 1. So we do 1 minus this probability that z is less than 1.94. And that that's this part right here. Okay, so it's 1 minus that. So then you look up your table for that, and this is 1.9. Remember the first 2 digits? And this is 0.0, remember? And then the last digit, see that is 4 right there in the hundreds place. So yeah, so if you add 1.9 plus 0.04, see how that gives you 1.94. Okay. All right. So now we're going to use our table. So I want the positive side of our table. Where's our table? Our standard normal table. You want the positive side because see how this is to the right? To the right. If you were using the negative, it'd have to be to the left of mu, but this is to the right of mu, so it's 1.9. 1.9, and then that 0.4, right? 1.9, and then that 4. So see, this is 0, 1, 2, 3, 4. Okay, so wouldn't it be that number right there, class? 1.9, right? 1.9, and then 0.04. Okay, and that would give you, see, 0.04, 1.9. So that's this 9738. 9738. Okay, so now we're doing some subtraction. 1 minus that area, 9738. Because you see, that's this area here, 9738. So the whole area, you know, the whole area beneath the curve is 1. And you're doing 1 taking away this, and that'll leave you with this. So 1 take away 0.9738 is 0.0262. Okay, and that's what goes here. Okay, and that's this area there. That's that area there. Okay. Now, that's using the table. Now, if you're asked to demonstrate it using the TI-84, so this is like part 2, which is the picture. Then here we use the table. Okay, here we're using the TI-84. So these two are the same. These two start off the same. But now we're going to use the calculator. So we don't really need this now because we're going to use the calculator, not the table, but we need the command. And the command is number 2, normal CDF, and then it's lower bound, upper bound, mu, and sigma. Okay, so we have normal CDF. Okay, so when we do the lower bound, we're talking about this shaded region here. So lower bound is this. This is our lower bound here. 1.94, and you read it from left to right. And then upper bound is, this is infinity. And you know, infinity is either 10,000 or you can use 1 E99. And if you use the E99, that uses the second and the comma. If you look at your second and your comma, second and comma, that has the EE on there. Okay. So we have 1.94 and then 10,000. You can use 10,000 or 1E99. And then mu is 0 and sigma is 1. Okay. So, and when you're using your calculator, that's the second vars, second vars. So that would be second vars would be second and then vars right here. And you want number two. Okay, and then I'm going to use it's 1.94. And then I'm going to use 10,000. And then 0 and 1. Okay, so you see that looks familiar, right? 0.02618977755. Now, if you use the 1E99, it's second vars, number 2, and it's 1.94, and then it's you would type in 1, and then the second, and then hit your comma because the comma has that EE, but it only types 1E here, okay, which is all right. And then 99, that's a very large number, 0 and 1. And you see we get the same thing. And then this is areas rounded to the 10,000s, 4 decimal places. The area underneath the curve is 4. It's not a Z. If it were Z, it'd be 2. But 1, 2, 3, 4. It's an area. All the areas underneath the standard normal, all these areas are to 4 decimal places. Okay. So 1, 2, 3, 4. Is that neighbor 5 or more? Yep, it's an 8. So add 1 to that. 0.0262. You see, and that matches what we got using the table method. Okay, so I'm required to show you both. And then on the test, on some problems, you'll be asked to use the table, and on some problems, you'll be asked to use the calculator, and then just follow directions. And also, when you do your homework, if they ask you to use the table, use the table. If they ask you to use the calculator, use the calculator. Majority of time they're going to come out the same. There's just a few special cases when they're off on the last digit, and that's why I have to show you both, because there are a few certain special circumstances where it's off just by a little bit, but you know the computer won't mark it right even if it's off by 10 thousandths of a point, right? 10 thousandths of a point by 0.0001, it still won't mark it right, right? So that's why I have to show you both. Okay. All right. So that's the idea of the central limit theorem. You have a new formula, and you use a new variable n. But other than that, you see how it's very similar to what we did in 6.2. See that? All right, so let's just try another one. So that one, this was area to the right. Now I think the next one is going to be one that it's sandwiched in between. So let's show you one of those. And like I said on the last page, I don't go over the last page. We don't make use of that. So it's optional. So I'll put optional here. We don't, majority of faculty don't cover that. It's not in the homework or the final. Okay, here's another one. Let's see. So it says that this is on page 155, vehicle age. The average age of a vehicle registered in the United States is 8 years. So that's your mu. So the only thing is that notice how it doesn't say 8 down here. Notice how it says that 96. And the reason why it says 96 is because that's in months. So you know that 12 times 8, because there's 12 months in the year, and there's 8 years. So 8 times 2 is 16. That's where they're getting 96 from. And the reason why they're putting it in months is because everything has to be in the same units. And so if you keep reading, it says that assume the standard deviation is 16 months. So since you have years and months, you want to put everything in the same unit, and we usually put that in the smaller unit. So the smaller unit between years and months would be months. So we put everything in months. And if a random sample, so that's a keyword, random sample of 36. So n is equal to 36. Find the probability that the mean of their ages is between 90 and 100 months. So here's 90 months. So I'm going to call that X bar 1, and then 100 months. So I'm going to call that X bar 2, subscript of 2. Okay, so we're going to have to use this formula twice, this new formula, and this is an area that's sandwiched in between. And so we're looking for this. It says find the probability, so we're finding the area. So area equals question mark. Okay. And we're going to run into the formula. So I'll put the formula at the top. Z is equal to x mean minus mu divided by sigma divided by square root of n. And I'm going to we're going to use the formula twice, new formula twice. Because we've got to run them through for both of them, okay? For find these z's. And in our picture, or let me do a sketch up here of our picture. So in your picture, your mu will be 0 and your sigma will be 1. And then right here, let me draw this here. And this is going to be like z sub 1 equals, and then we're going to find z sub 2 equals. So this is z sub 1 and z sub 2. Okay, so we're going to run that through. Run that through. Okay. Okay, so then in our formula, we have z sub 1 is equal to x sub 1. I'm going to do this one first. So that looks like 90 minus mu is 96, right? This is 96. Close parenthesis. Open parenthesis. Sigma was 16. Divided by the square root of n was 36. And close it. And you know, the square root of 36, do you know that already by heart? Do you know that the square root of 36 is actually just 6? If you the other one wasn't a perfect square. I think the other problem that we did, it was it square root of 20 a while ago? Yeah, that wasn't a perfect root. Square root of 20 is not perfect. But square root of 36 is, watch, if I do second and then x squared, 36. See, that's a perfect square. A while ago we had square root of 20. See, that's not a perfect square, but the square root of 36 is. See that? So I can just also use 6 in there. So when I type this in, so I have open parentheses, 90, take away 96, close parentheses, divided by open parentheses, 16. And you can just say divided by 6 because we said that square root of 36 was 6. So that's just, and then close it and then hit equals. And you get negative 2.25. Yeah, and if you don't want to do that, that's fine. Then you've not 90 minus 96, close parentheses, divided by open parentheses, 16 divided by second, and then x squared, and then 36. But then you're going to have to remember to hit this little arrow right here, and then close the parentheses. Parentheses are on top of 8 and 9. And then you still get the negative 2.25. Okay, so now here on the picture, I can put here negative 2.25. Okay, now do is find the other one, z sub 2. So now it's this x sub 2 right here, x sub 2 right here is 100. So 100 and minus 96 divided by 16 divided by square root of 36, which we know to be 6. Okay, so there the only thing that changes is your x bar is the other one, which is the 100. Okay, so then I have open parenthesis 100 minus 96 close parenthesis divided by open parenthesis 16 divided by, and again you can say 6 square root of 36 is 6. Okay, or you can do 100 minus 96 close parenthesis divided by open parenthesis 16 divided by second and then x squared and then 36. But then you have to remember, see that? Push this arrow right here and then close parenthesis equals. And you see we still get 1.5. All right. Okay, and then that goes right here then. That's right here. That's for this right here. Okay, so that's your new picture. Okay, so now we're going to use the table. So that's like part 1, finding those. Okay, now we're going to find the area. So we have probability. First it started off as x bars and they were stuck. They were sandwiched between 90 and 100. Okay. Okay, then we ran it through the formula and then they became z's. And now we have it between negative 2.25 and 1.5. Okay, and then we're going to use the table. And this is sandwich. So in the table, you have to do the larger area minus the smaller area. So the larger area is, and remember, don't look at this picture anymore, look at this. The larger area is probability that z is less than 1.5. Take away the smaller area. So this is the larger area, all this. And you're going to take away the smaller area, probability that z is less than negative 2.25. So you've got this larger area here, which is this here. And then you're taking away the smaller area here, which is this part here. And then that's going to just leave you with this part here. That's going to leave you, when you do this larger takeaway, that's going to leave you with just this part here. Okay. All right. So then in our table we have z, and remember this is 1.5. And if it helps you, you can put a 0. There's not a digit there, so it's like a 0. But the first 2 digits is 1.5, and then remember you have to put 0 and then the last digit. There's just not a last digit there, but it's really a 0. So it's really 1.500. Whereas this one over here, it's negative 2.2 and then 0.0, and the last digit is 5. Okay. Okay. So when I look them up on the table, I'm looking up 1.5. I'm on the positive side. So go to your positive table, look up 1.500. See 00 is here, and then 1.5. There's 1.5. Okay, see that? See that 0.9332? 0.9332. Okay, 0.9332. Okay, the other one is on the negative 2.25. So I hope y'all saw that. 1.5 and then 0.00. So that's this right here. Okay, now I'm going to have to go to my negative side of my table. Go to the negative table. Go to the negative standard normal table. And you're looking up negative 2.2. See? Negative 2.2 and then 0.05. Okay, so remember, you know, if this is negative, remember these are negative. So I like to put little negatives on mine. Okay, so negative 2.2. So it looks like it's this, let's see. Looks like it's this right here, right? 0.0122, right? 0.0122. So there's a negative 2.2 right here, and then the negative 0.05. So that's this right here, 0.0122. 0.0122. Okay, and then we're going to subtract. Okay, so the larger area, so I'm subtracting 0.9332 minus 0.0122. So I have 0.9332 minus 0.0122 is 0.921 and then the 0. Okay, class. So did y'all get that then? So you're subtracting those, and that would be the area. That would be this area here. That would be, oh, and that's the area, but I probably should put it over here, right? That's this area over here, 0.9210. So 0.9210. Yeah. I mean, I guess I could put it here too, but you know, I have my new picture, so with the Z's, so I feel more comfortable putting it there, but that's that area reflective of that in the center there, okay? Okay, now let's see, where can I squeeze the other one where you do the calculator? Let's see, I'm running out of space. So this part would be the same. This would be the same. And then what's different is this would be your calculator command, but this part would be the same. So you would still start off with probability, and these were X bars, those sample means that were stuck between 90 and 100. And then you ran it through the formula, and now they became Z's, negative 2.25 between that and 1.5. But then you use a calculator, and that's where you use that 2 normal CDF, lower bound, upper bound, mu and sigma. And when you do that, your lower bound and your picture. So remember, we're not, be careful, you're not looking at this. Remember, you don't want to grab those numbers by mistake. Remember your 0 and 1. Remember mu changed to 0 and 1 because you ran it through. You want to use these numbers. So this is your lower bound. This is your upper bound because you regraph from left to right. So this is your lower bound and this one here is your upper bound. So you have negative 2.25. And then your upper bound is 1.5 and then 0 and 1. And remember that's a second vars. Second vars. So when you do that on your calculator, second vars. So here's your second, here's your vars. Okay, so second vars, and then you want number 2. So scroll down to number 2, hit enter, normal CDF. Okay, and then the lower bound is negative. So don't forget your negative is down here. Negative 2.25. Enter upper bound is 1.5, 0, and 1. Okay. I'm going to hit enter. I'm going to hit enter again. Okay, so that's 0.9209683379. And remember, areas are to 4 decimal places. 1, 2, 3, 4. And look at the number to the right. Is that 5 or more? Yep, that's a 6. So add 1 to that. Okay, that's a 6. So add 1 to that. So 9 and 1 is 10. Carry 1 again. 0 and 1 is 1. And then that's 2 and that's 9. Decimal 0. And you see that's the same as what we got earlier, right? See this somewhere down here, see? 9210. So it's the same. Okay. All right. Okay, so basically I have one more problem to show you, but I do like how I'm going to show you this one too, because they're reminding you, this is related to section 6.2. And then this one down here, it's problem related, but this is section 6.3, central limit theorem. So I'm going to go work both of them, but this is section 6.2 and this is section 6.3. So you can see here it says working weekends, the average time spent by construction workers on weekends is 7.93 hours over 2 days. So you can see the 7.93 hours here. And this is your mu. And then you can see down here they have that also. That's the same for both problems. 7.93, and this is hours. Assume the distribution is approximately normal with a standard deviation of 0.8 hours. Okay, so I'm putting that on both of those diagrams. Sigma. Find the probability of an individual. See, find the probability of an individual, see, who works that trade. Find the probability an individual who works that trade works fewer than 8 hours on the weekend. So you see fewer than 8. So here's 8, okay? And in 6.2, that was what we call X, right? That was X. Fewer than 8 hours, so you're shading this way. But it's an individual. Whereas in the central limit theorem, it says if a sample of 40 workers, so here n is 40, is randomly selected, find probably the mean, see, the mean of the sample, it'll be less than 8 hours. So see, this is 8 also, but this is X bar, the mean of the sample. See that? So this is 6.3. So here we've got to use the formula, the sample means minus mu divided by sigma divided by square root of n. But over here on top, for this one, here we have to use the new formula, where here we use the original formula, and that would be the one from section 6.2. That would be this one, remember? Z is equal to xc, x minus mu divided by sigma. Okay, so then here in this one, x is 8 minus mu is, what was that, 7.93 over sigma, and sigma was 0.8. See that? Whereas down here, your x bar is going to be, see right here, 8 minus mu, which was also 7.93, and then sigma is 0.8, but then c divided by c squared of n, which is the new formula has n, which is 40. Do this and then close it. See that? So you have to be careful. Okay, so if it's an individual, it's section 6.2. And then when they have this variable n, it's central limit theorem. Okay, so I do like how they have that side by side, how those varies. Okay, so then let's find both these z's then for these problems. So over here we have 8, parentheses, 8 minus 7.93 close parentheses divided by 0.8. And that looks like it's 0.0875. And that's a z, so round to the hundreds. And look at the neighbors at 5 or more. Yep, it's a 7. So it looks like that z is about 0.09. Let me just check that on my paper here. Yes, okay. Whereas on the bottom, this one down here, this one is parentheses 8 minus 7.93 close parentheses divided by open parentheses 0.8 divided by second square root, right? So second x squared, and then that was a 40. So here you have to remember to push this little arrow out like that and then hit the parentheses and then hit enter. And that gives you 0.553398595. And you're rounding to nearest hundreds, tens, hundreds. And then look at the number to the right. Is that 5 or more? Nope, that's a 5. So it's about 0.55, and that's your z for that. Okay. Now you have your new pictures, and your new pictures. This picture would be so remember mu is 0, and remember sigma is 1, and then now this is now a z, which is here 0.09. Okay. Whereas over here, this new picture, mu is also 0 and sigma is also 1, even the central limit theorem, that's the same. And then here, when you got your z here, because you use a special new formula with square root of n, that gave you 0.55. See that? Okay. And then now we're going to find our probabilities, find the probabilities, find the area underneath the curve. So for this one, we have probability, and first this first started off as an X. This one started off as an X bar, but this one started off as an X because this is central limit theorem and it had the mean, sample mean. This one is just X and it's less than 8. And then we ran it through the formula and now it became a Z and it's less than 0.09. And this is the easiest one because it's already area to the left. So when you look up, it's 0.0, remember the first two? And then this is 0.0 and then 9. Okay, so when we look that up on the positive side, 0. So see, 0.0 and then 0.9. So I don't think I really need a ruler for this one, but see 0.0 and see way over here. It's that number. Can you see that number? See that 0.53, see 0.0 and then 0.09. 5359. 5359. 5359. 5359. Yeah, so that would be it. That's that. So that's the easiest type because this one, because this is already area to the left of the curve, it's not like you like sometimes if it's sandwich, you have to do the larger minus the smaller, or if it's the area to the right, you have to do 1 minus the area to the left. But this is the easiest type because it's already to the left. Okay, and then that's using the table. Okay, we'll go back and do the calculator in a little bit, but let me just go to this one now and do the table. So here, probability, this is X bar. So here, X bar is less than 8. And then you ran it through the formula, it became a Z. It's less than 0.55. And then when you look it up on your, 0.5 on your table, 0.5 and then 0.05. Okay, so 0.5 and then 0.05. Okay, and let's see. I'm gonna finish the video recording, but I'm gonna just I'm going to leave this camera off real quick, and I'm gonna redo this real quick. I'm gonna continue it. Okay, so I hope you can hear me. Hope you can hear me. Yes? Okay. So I'm gonna just leave my camera off, but I hope you can hear me. I'm gonna finish this. So I'm looking at the table on the positive side, 0.5, 0.5. Okay, so here's 0.5. And then I went 0.05. So 0.05. Okay, so here's 0.5, 0.05. See that number right there? 7088. 7088. 7088. Okay, so I hope you can see that. So 0.5 and then 0.05. 70, 88. Okay. All right. So that's what this is. Okay, now we're going to, on both of these, I'm going to show you, that was using the table. So the last thing I need to do is show you using the calculator and using the normal CDF. Okay, now this one, let me do this one last because I have lots of space. I'm going to run out of room on the other one, I think. But for the TI-84, remember this would be the same. Probability X bar is less than 8. Probability Z, because you ran it through, is less than 0.55. And then you remember we're using two normal CDF, lower bound, upper bound, mu, and sigma. So normal CDF, lower bound. So remember you read graphs from left to right. But remember, be careful. You're not reading the original. You're reading this one. So be careful because this is negative infinity, which is negative 10,000, or negative 1 e to the 99. Okay, so you left to right. You read it from left to right all the way to 0.55. So you have negative 10,000 all the way to 0.55. Mu is 0, sigma is 1. Okay. Okay, so on the calculator, you're doing a second bars. Doing a second bars on the calculator. Okay, so second bars, number 2. Okay, and then your lower bound is a negative 10,000. And then 0.55 is your upper bound. And you don't have to put that 0 there. And then 0 and 1. Okay. And then you see this number right there? 0.7088. So write that down. So then you record to the 10,000s. 1, 2, 3, 4. That's right here. The 8, look at the number to the right. Is that 5 or more? Nope. So that stays. So 0.7088. See how that matches this? So this matches that. Okay. All right. Okay. So if you don't want to use a negative 10,000, you could do negative 1 E 99. Okay. So if you do that, you do second bars, normal, number 2, normal. Put a negative 1, negative 1. Okay, and then second comma, because that's where your EE is at, except it records 1 E, and then 99. Okay, and then there's your 0.55, 0 and 1. Okay, but see how we got the same thing? Okay. Okay, so the last thing I need to do, last statement is, I don't know where to put it because I'm running out of room, but the last thing would be to do this again using the TI-84. So I think I'll just, because I'm running out of room, I'm going to just put the command. This is going to be the same, and this is going to be the same. Okay, but then on the calculator command on the TI-84, you would do 2 normal CDF, and you know it's lower bound, upper bound, mu and sigma. Okay, so because I'm running out of space, I'm going to just put the lower bound. So here, the lower bound, remember you want to be careful not to look at the original, but look at this. So lower bound, you read it from left to right. So it's negative infinity all the way to 0.09. So you can use negative 10,000, and then that's your lower bound. And then this is your upper bound, 0.09. And then sigma is 0. Mu is 0, sigma is 1. Mu is 0, sigma is 1. Okay, so then when you do that, you have number 2, second vars, number 2. Okay, so you have negative 10,000, and then 0.09, and then 0 and 1. Okay. And we should get, should match what we got over here. See that? Okay. So we have 0.5358564569. So 4 decimal places, 1, 2, 3, 4. Okay, look at the number to the right. Is that 5 or more? Yep, that's an 8. So add 1 to that. So there's your 0.5359. And you see that that matches this right here. See? The same. Okay. All right. Okay. Okay, so go ahead and finish your online homework for this section 6.3, the central limit theorem, and then you need to get ready for your test. So I'll do a recording for the test review. You can use a test while you're taking the real test. You can use the practice test, but you need to get ready after you do your homework to do your practice test. Okay? And then we'll take that test 3. And then after test 3, there's a quiz 3, and then the final. So we're almost done. So hang in there. Okay, good luck with your studying.